Hello, everyone. We'll get started in just a minute. Um, as we're waiting, if you have any questions about stuff from previous lectures, feel free to ask. So we're going to try to do something slightly different with the quizzes this time. So when for the quizzes, I'll show the answers, and then we'll just give everybody 15 seconds to think about it before we start typing into the chat, just to make sure everyone's had a chance to consider. Yeah, otherwise this will be, I'll try to do it similar to the last one. So we'll have breaks at the quizzes when I'll try to answer questions. Feel free to ask questions at any time. I might just batch them up to answer them when there's breaks. Yeah, and let me know if you have any questions about other class logistics stuff. I'll have lab 10 up later today. At least the first half of that lab is covered by this lecture, so you could get started on it if you want. After Thursday's lecture, then you'll have all the material. All right, let's go ahead and get started. Okay, so today we're going to be talking about a new kind of statistical test called a chi-square test or a chi-squared test. And so just to review where we are here, right, part of doing a null hypothesis significance test, really the hard part of doing a null hypothesis test is that we need to figure out what our null distribution is, right? So whatever kind of statistic we're measuring in our data, we want to figure out what the distribution of that statistic would look like if the null hypothesis is true. And so we've talked about a bunch of ways for doing this. So if we have scale data, for example, we could use a t-test. We could use a permutation test, right, to mix between groups, for example. We talked about rank tests for ordinal data. And again, we could also use these for scale data since we can also sort scale data. But one thing we haven't talked too much about yet is nominal data, right? And so if we're just getting responses from people that aren't ordered in any way, so we can't compute even a median of these responses, how can we look at these? How can we look at what the null distribution is? Okay, great. Saw in chat there about a delay, but I'm glad that's fixed. So if you think back to like some of the first weeks of the class, we were talking about one type of the sort of simplest type of data we can get is just categorical data, where for every participant, for example, we're asking them to choose among several options. And these are options that can't be ranked, so we can't really do any kind of arithmetic on them. But we would still like to be able to ask some kind of null hypothesis questions. And so one kind of question, for example, would be asking whether the counts that we're getting, so the chance of people picking each of these options, is it consistent with some kind of null hypothesis that we have? So, for example, a null hypothesis might be that all of the responses are equally likely. We could also have more complicated kind of null hypotheses. Maybe we think that everyone is going to pick one option, right? Or maybe 90% of people are going to pick one option. Another kind of question we might want to ask is if we have multiple nominal responses from the same subjects, we could ask how those responses are related to each other. So, for example, if we know the gender of each of our subjects and we know their favorite color, we could ask whether those two responses are related to each other, right? It's kind of like the idea behind a correlation, right? But we can't really do a Pearson correlation here because these are just nominal measurements. So the null distribution we're going to make use of here is called the chi-square distribution. This is not a very well-known distribution, but it is a very useful one. We're going to use it today, and it's also kind of the building block for some stuff we're going to do in the next few weeks. But yeah, it's not like a name that you've probably heard of before. And so the way we generate it is by taking samples from a normal distribution. So we take a sample from a normal distribution, we square that sample, and then we take another sample from a normal distribution and square that sample. we do this k times, and then we add up those k squared values. Right, so this is a distribution of what you get if you take sums of squared values out of a normal distribution. That's sort of where the square is coming from in the chi-square name. And this might seem like a kind of weird thing to do. As you'll see, this ends up being the kind of natural null distribution for what we want. And so there's a bunch of ways that this distribution gets used besides what we're going to talk about today. So one, for example, is when we're thinking about trying to model uncertainty and variances. Right, a variance is basically something like sums of squared deviations. And so if our deviations are normally distributed, then variances, our sample variances, will have a chi-square distribution. We're going to use it on Thursday to construct the F distribution. So I'll just leave that till then to describe what that thing is. And you can also use it to, there's a number of different hypothesis tests you can use this for. We're going to talk about the simplest one today. Okay, so we talked at the beginning of the class about probably the simplest kind of descriptive statistic that we can get from a data set, which is just what we call frequency, which is just the number of times that an outcome occurred in a data set, right? So it's not even, in other kinds of science contexts, the word frequency means like some kind of normalized rate or something. Here, the word frequency just means a count. So it's like the tally function in R. We're just counting up how many times each outcome occurred. And this is pretty much one of the only statistics we can compute for nominal data, right? We can't do any kind of math on it. All we can really do is just count up how many responses of each type we got. And so just to refresh your memory on some other terminology, right, we also talked about proportions, which are the fraction of the samples in the data set of each type, right? So if we want to get the proportion of people that answered red as their favorite color, we would just count up the number of people that answered red and divide by the total sample size. And this proportion is different than the probability, because the probability is this population parameter that we can't directly observe, right? So proportions are things that we're measuring in data by counting things up and dividing by n. And probabilities, we don't ever know the true underlying probabilities, but we could approximate them with these proportions, right? So if we compute this proportion in our data, which is this descriptive statistic of this particular sample, it should be approximately equal to the underlying population probability. And of course, how tight this squiggly equals depends on a lot of things. It depends on, for example, the sample size. It depends on how small these probabilities are, right? So small probabilities are going to be harder for us to estimate accurately. And so here, instead of having null hypotheses about means, our null hypotheses are mostly going to be about probabilities, right? So we're going to have some starting hypothesis that there's a particular probability in our population, and we want to check whether our proportion that we're getting is consistent with that probability. And so, yeah, there's a question in chat that proportion is like probability in a sample, which is right. So proportions are right a descriptive statistic we can measure that allows us to approximate these probabilities. Part of the reason we try to use different words here for the descriptive thing and the population thing is that the probabilities are often going to come out of some kind of math. So like we're going to get some kind of null distribution by doing some kind of mathematical manipulation of probabilities. Whereas the proportions are coming from this other direction, which is just counting things in the data. And what we're hoping is that the two of them will meet, right? That the things we're measuring in the data are going to match up with something that we're deriving from the math. And so, so you could think of proportion as just like the sample version of a probability. Okay. And so kind of similar to probabilities, we can also think about a a population level statistic that we can measure that has to do with frequencies. And so I'll write this as E of Fi, right? That which means the expected frequency of outcome I. And so there's nothing complicated here that's happening, right? All we're saying is that if you know what this probability in the population is, if we have some hypothesis about what this probability in the population is, we can also figure out how many responses we expect to get of type I, right? And so, right, if you just look at this equation here, all we have to do is, like, if we know the probability, we just multiply by n to get this expected number of counts. I'm going to try to just write this with the subscript I whenever I'm writing it, just to keep track of which ones we're talking about. And so our null hypotheses are usually going to look something like this. So we could write these in terms of probabilities. To do the statistical tests, it's usually easier to write these in terms of frequencies instead. But right, there's really, conceptually, there's not much of a difference, right? We can either our null hypothesis can say what fraction of responses we expect to be of type I, or our null hypothesis can be about how many responses of type I we expect there to be. The actual like math of the chi-square test assumes we're working with these frequency counts and not the probabilities. Okay, let's take a quick quiz break, and again, feel free to is correct. A, by counting outcomes in our current data set. B, from a null hypothesis about the outcomes. C, by assuming all outcomes are equally likely. Or D, by setting it equal to n. So I'll just give you a few seconds to think about it. All right, now you can go ahead and type what answer you think it is into chat. All right, I see some B's and some C's. Yeah, people are pretty split. So C, it can often be the right answer, which is that our null hypothesis is that everything is the same, but it doesn't have to be, right? So in general, we get this expected frequency from some kind of null hypothesis about our outcomes. Often our null hypothesis could be that the outcomes are equally likely, but that doesn't have to be the null hypothesis. Right, so for example, we could have there's maybe some baseline kind of responses that we expect, and we want to see whether it differs from that baseline, and that baseline doesn't have to be all equal. We'll do a couple examples today. One of them is that it's all equal, and one of them that it's not. Okay, great. All right, thanks so much, everyone, for responding. It's just nice to see people in chat. Okay, so we have actually talked about this a little bit back a few weeks ago in the context of the binomial distribution, right? So we talked about, we were using the example of trying to figure out whether there's an elevated level of schizophrenia in the Bronx compared to some baseline level, right? And so that's a case where we have a nominal outcome, which is each individual person's diagnosis. And we were trying to test whether the number of schizophrenia diagnoses that we were counting in that population, whether it's different from what we'd expect from some baseline null hypothesis. But often we're going to have more than two outcomes in our nominal data. And so for that, this binomial distribution doesn't really apply. So for example, let's imagine that we're looking at a die that has 6 different sides on it, right? And so we're going to look at instead of just looking at like the number of times that a 1 comes up or a 2 comes up, we're going to look at all of the outcomes at the same time, right? So we're not just going to say, is this a 1 or not? We're going to ask how many 1s, how many 2s, how many 3s, and so on, right? And so in any particular, and so in our particular sample, we can count up how many of each of these outcomes there are. So right, there's 6 possible outcomes here. In f sub I is just a made up example of what we might get in a particular sample. And then our expected value of fi is what we'd expect under the null hypothesis. And so here we have a boring null hypothesis, which is that all the outcomes are equally likely. And so if we roll the die 120 times, then we should get 20 of each value, right? That's what we'd expect under the null. And so the question is, we got these 6 actual frequencies, and the question is whether this is surprising or not, right? We can see some of the numbers are kind of pretty close to 20. We got like only 13 5s, right? And the question is that weird? Is this something that's inconsistent with our null hypothesis or not? Right. And so what we want to come up with some kind of statistic that compares our actual frequencies in our sample to these null expected frequencies. And then we need to figure out what that distribution would look like if the null hypothesis is true, right? So if the null hypothesis is true, we wouldn't expect to get exactly 20s, but we should get things like pretty close to 20. And so we need some kind of statistic that says how close to 20 are these outcomes, and are we like surprised at how far away it is from 20? And so yeah, we haven't really talked about a good statistic yet for doing this. We can't like really compare a median or a mean here. We can't just like, right, in the binomial distribution, we said there were like successes and failures, but that doesn't really work here because there's 6 outcomes. And so what we're going to try to do is, one way to think about this null hypothesis is that the difference between our counts in our data and these expectations should be 0, right? And so these deviations from the expected values are basically the thing that we want to measure, right? And we need to, again, have some way of formally defining like what counts as a big deviation from the null. So there's a few ways you could write down, there's a few different kinds of statistics you could come up with here. The one that has the nicest properties that fits in with this chi-square distribution is to think about doing sums of squared deviations. And specifically to sort of normalize this out, we're actually going to compute it like this. So this symbol on the left is the chi symbol. It's just like a squiggly X. And so we write chi with a superscript 2 to indicate this is a chi-squared statistic. And so to compute this, what we do is we take all of the deviations in our data. So we take our actual measured frequency of a particular outcome and subtract our null expected number of counts. That gives us this deviation. We square that deviation and then divide it by the expected number of counts. So this is kind of normalizing things, right? It's telling us like what % off from the expected value are we? And then the sum here is summing over all the possible outcomes, right? So we have, if we have k possible outcomes, we compute these squared and normalized deviations for each outcome and then sum them up. And so if we compute the statistic in this way, then these chi-squared values are sort of proper chi-squared values that have a chi-squared distribution. And that means that if the this resulting sum, if the null hypothesis is true, this resulting sum is going to have a chi-squared distribution. And so again, just like we've been doing for all of these null hypothesis tests, right? We can measure this statistic in our data, ask how far from the expected counts are we? And then we can use the chi-square distribution to ask whether that's a surprising amount or not. So one thing that's really nice about this is that this equation works for just about any distribution over our outcomes. So it's kind of related to the central limit theorem, basically, that if no matter what the actual underlying probability distribution is across the Fs, this chi-squared statistic will have a proper chi-squared distribution. And so, right, just the same way that as long as our sample is big enough, the sampling distribution of means tends to be normal. The sampling distribution of this chi-squared sum of squares thing tends to have a chi-squared distribution. And so that means that we don't have to have strong assumptions about what these distributions look like. Our null hypothesis might be kind of something complicated about what these frequencies are. That doesn't really matter. We can still compute this kind of statistic. So yeah, there was a question about what K is here, right? And so whenever we have a nominal outcome, the number of possible outcomes is K. So K here is not like the number of subjects, right? This is if we ask people about their favorite color and we give them 5 choices for their favorite color, K would be 5 here. In the die example we did, K is 6, right? There's 6 possible ways that there's 6 possible outcomes of a single trial when we roll that die. And so to compute the statistic, we would compare each of the frequencies of our die to these expectations. So we're going to work that out in just a second. Okay, take another quick quiz break. So the chi-squared statistic is either A, can be positive or negative. B, cannot be computed. It's just a population thing we have to infer. C, measures the difference between the data and the null. Or D, should be exactly 0 if the null hypothesis is true. All right, go ahead and respond. Okay, great. Yep, seeing a lot of C's, which is right. The chi-squared statistic is measuring these normalized squared deviations between the data and the null. It can't be negative. It's always going to be a positive value, right? It's the sum of squared deviations. It is a descriptive statistic we can compute on our data set. And it'll never be exactly 0. Well, it'll almost never be exactly 0. Even if the null hypothesis is true, we'd expect that usually there's going to be some small fluctuations away from our expectation, right? So what we're going to need is a chi-squared distribution to tell us how big should we expect this statistic to be if the null hypothesis is true. Okay, so let's work this out for our die example. So here are here's the data I was showing before. Right, so we have, again, the expected frequencies here are coming from our null hypothesis, which in this case is that we should get it about 20 in each of each outcome. So the first thing we do is compute our deviations. So for every outcome, we compare how many we actually got versus how many we expected. We square those deviations and then divide them by the expected frequencies, right? And so this is giving us these kind of like relative deviations from expectation. So to get our chi-squared statistic, all we do is sum those up across our k different outcomes, right? There's 6, k is 6 here for 6 different outcomes, which gives us a chi-squared statistic of 4.15. Now, again, that's not super meaningful, right? The question is whether that's big or small. So what we need to know is what's a kind of critical chi-squared statistic here that would be big enough for us to reject the null hypothesis, right? Are these deviations, the sum of squared normalized deviations, are these big enough for us to actually say, we think that the true underlying distribution of this die is not a fair, equally probable outcome across all the outcomes. So just like with many of these tests we're doing and we'll continue to do, we need to know the degrees of freedom. There's actually more than one chi-squared distribution, and we need to know which one we're using. So there's basically a bunch of different kinds of chi-square tests. And so what we need to know is this anytime we're running chi-square tests, we need to specify these expected frequencies, and we need to figure out what the appropriate degrees of freedom are. And so we did part one, and we just need to figure out this part two part. And so here's an example of what these different chi-square distributions look like for different degrees of freedom. So if you remember, like for t-tests, for example, the degrees of freedom had a like sort of small impact on the t distribution. It just changed like how much stuff was out in the tails, in the whether the tails were sort of heavy or they looked more like a normal distribution. For chi-square distribution, that's not true. The degrees of freedom really change the shape a lot. But you can see, at least once you get past the smallest numbers, it turns into this like kind of smushed out looking thing. It's not symmetrical, right? It has this, it's positively skewed up here to the right, and it's never negative. And so, so how do we know which of these distributions to use? So just to remind you about the terminology here. So we are, in this experiment, we are measuring a single factor, meaning a single nominal outcome. And there are 6 different levels of that factor, which just means that there's 6 different possible responses for that this one factor that we're measuring. And so we're going to use in this case a one-way chi-squared test, which just means it's a chi-squared test for a single factor. And the degrees of freedom here is simply the number of levels of that factor minus 1. The logic of this is kind of similar to the same reason that the degrees of freedom in a t-test is the number of subjects minus 1, right? So notice here, first of all, this is not number of subjects, this is number of levels. But the logic is kind of similar that, right, if we know how many, if we know the responses, if we know how many 1s, 2s, 3s, 4s, and 5s there were in our data set, we can figure out how many 6s there were because it has to all add up to n, right? So there's kind of one less degree of freedom than the number of outcomes. So yeah, at this point you would either use R or a table or something and ask for a chi-square distribution with 5 degrees of freedom, right? 6 minus 1. Then how big does this chi-squared statistic have to be for us to reject the null hypothesis at a 0.05 level? And the answer is 11.07, right? So we're not that close to that, and so we would fail to reject the null, right? Meaning in this data, we don't have strong evidence that these dice are loaded, right? We don't have strong evidence that this die is actually doing something other than just the null equal probable outcomes. You can notice here we don't have to actually specify whether this is a one-tailed or a two-tailed test because for these chi-square tests there are only one-tailed tests, right? There isn't like a direction here in our test because right, their outcomes are not ordered in any way. And so the statistic just sort of starts at 0 and then just gets bigger and bigger as things get more and more surprising. So all that we're measuring is the area that's more positive than our chi-squared statistic. Okay, so yeah, so there's a question about how we get these critical values. So yeah, so to get this value, for example, you could look up in a table. So in the homework that is due next week, there's a little table attached which you can use. And of course, in practice, when we're actually doing this, we would just usually have R look it up for us. Okay. All right, here's another quiz about the degrees of freedom for our chi-square distribution. Do they A, shift the critical chi-square threshold for rejecting the null, B, depend on the sample size, C, they can take non-integer values, or D, they can't be computed until after you've already collected your data? All right, you can go ahead and type into chat. Okay, I'm seeing some A's and some B's. Um, so B would be the correct answer for things like a t-test, right? Where the degrees of freedom are like the number of samples minus one. Here, though, the correct answer is actually A, right? So the degrees of freedom here are the number of levels of this outcome minus one, right? So in our die case, we rolled the die 120 times, right? But the degrees of freedom is not 119, it's 5, right? This is pretty confusing because this formula looks very similar to the t-test one, but it's actually quite different, right? The t-test one is the number of subjects minus one. Here, this is the number of outcomes minus one. So the number of the actual sample size is actually not super relevant here. We'll talk about this in a little bit when we talk about the assumptions, but we basically just need the samples to be, we need the sample size to be big enough that this chi-square distribution, like actually that these chi-squared statistics actually converge to their to the chi-square distribution, which again is a kind of central limit theorem kind of result, and doesn't usually take that many samples. So as long as we have something more than like 5 or 10 of each possible outcome, then that assumption is guaranteed. So yeah, so the degrees of freedom here are about the number of levels minus one, not the sample size, right? So yeah, so the degrees of freedom here are going to change our chi-squared threshold, right? So if we look at these distributions, you can see that, right, if we want to know how big does a chi-squared statistic need to be such that the area beyond that statistic under the curve is less than 0.05, that threshold is going to move as these degrees of freedom change, right? And so for degrees of freedom of 1, for example, a chi-squared of like 3 or 4 is kind of impressive, right? It's hard to get beyond that in this null distribution. For a degrees of freedom of 10, 3 or 4 is not at all impressive, right? You need to be out here probably like 15 or so to be interesting. Yeah, there was also a question here that like why it seems like there's like a weird flip between 2 and 3 degrees of freedom, which, yeah, I don't know if there's like a super good intuition for why that is. Like if you look at the actual mathematical form of this, it makes a little more sense. There's like a weird normalization term here that'll flip when you go from 2 to 3. Yeah, I mean, it's really the impact it's having is on this like very tiny slice around 0, basically, which is that if you have only 2 degrees of freedom, getting these really tiny values is a lot more likely. You can see even between like 3 and 5, for example, there's also a big change in this region where, right, even for 3, it's still sort of possible to get chi-squared values that are less than 1, but once you're out here, it's very unlikely to get these really tiny values. Okay. So yeah, so just to review that one more time, right? The answer here is A, that degrees of freedom are depending on the number of levels, not the sample size, and are important for getting this threshold. Okay, so let's try a slightly more complicated version, which is that we're going to, instead of looking at a single die, we're going to look at a pair of dice. And so the game of craps, which I haven't actually played in a long time, I forget exactly how it works, but it involves rolling 2 dice and taking the sum of those 2 dice. So it doesn't matter. Well, I think in most cases it doesn't matter whether you're getting the number whether you're getting the number 8 from a 2 and a 6 or from a 3 and a 5, for example. And so what we want to know here is, let's say somebody is claiming they're rolling these dice and reporting the values to us, and we want to know, are they really rolling them fairly or not? And so all they're telling us is the sum of the two dice, and we want to know whether it seems like those are coming from fair rolls or not. And so the tricky thing here is that the null hypothesis is not uniform, right? So if you roll two dice, it's a lot more likely to get a 7 than a 12, for example, simply because there's more combinations of two dice that will give you a sum of 7 than a sum of 12. And so the expected frequencies look like this. So you could think about that, right? If you roll two dice, there's like 36 outcomes of 6 possible outcomes on one and 6 on the other. And if we look at the sums of the dice, the sums could be from 2 to 12. 2 and 12 are the least likely. There's only one way to get those. 7 is the most likely. There's 6 different ways to get a sum of 7. So if someone is just telling us that they're claiming they're rolling two dice, they're reporting these probabilities. They're reporting the sums of these on each roll, the sums of the two dice. What we want to figure out is whether what they're reporting to us is actually consistent with that null hypothesis or not. So we're going to have to get an expected frequency here by just taking these probabilities, multiplying by our sample size. You might notice this might give us things that are not whole numbers, but that's okay. Right? If our sample size is not a multiple of 36, we're going to get some decimals here, which is fine. Right. Also, remember here, the degrees of freedom here are going to be 10 because there's 11 possible outcomes from 2 to 12, right? No matter what our sample size is, degrees of freedom will be 10. Okay, so let's look at an example where we have 500 rolls, and we're going to, the first statistic we're computing here is just the frequencies, right? So out of these 500 rolls, we got two 10s, we got 35 3s, and so on. And so what we'd like to test is this data distribution that we see here, which is the top line, right? These counts that we see in our data. Is this consistent with someone that's rolling two dice fairly and reporting the sum? So we're going to compute this chi-squared statistic. Again, the steps here is we compute our deviations, right? So for every outcome, we compute how far off from expected are we. We square up those deviations and divide by our expectation, and then add up this across all of our 11 possible outcomes to get our chi-squared statistic of about 21. So again, degrees of freedom here is 10. And so for an alpha of 0.05, the critical value here is 18.31, right? And so what we found is that our chi-squared statistic, which again is measuring some kind of difference between our data and the null, is bigger than we'd expect. So we'd reject the null hypothesis that the dice are fair, right? Meaning that the person that's doing this must be lying to us in some way, right? That the values that we're getting are unlikely to have actually happened on fair dice rolls. We don't know for sure, right? I mean, even under the null hypothesis, it's possible to get a chi-squared of 21. But right, if the null hypothesis is true, this should happen less than 5% of the time. Right. And so this is pretty suspicious data, right? You can see some of these values, like we're getting way more 8s than we're supposed to, right? There's almost 20 extra 8s here, right? And so when we sum up these squared values, that sum is larger than we'd expect. Okay, so just to list out explicitly here what the assumptions are for these this kind of one-way chi-square test. So first of all, we are assuming that these data are random independent samples, right? Every sample is sampled uniformly from the population and doesn't depend on other samples. We need to write down some kind of expected distribution, which is often uniform but doesn't have to be. And we need our sample size to be big enough. And so this last one is the only one that's tends to be a potential issue if we're thinking about designing an experiment. And so there's a few things we need. I mean, first of all, we need expected frequencies to be bigger than 0. Otherwise, we're going to have like divisions by 0 in our statistic, which is going to be bad. And ideally, we'd want every outcome here to be like at least 5. So if we only have 2 possible outcomes, we want at least 5 or 10 in each of these outcomes. If we have a lot of outcomes, it might be hard to actually get 5 in every single square, but we want to have at least one in each square, and at least one in every possible outcome, and hopefully at least 5. The problem is if these counts are too small, then the chi-square distribution is no longer a good null distribution for this. And so we basically would just have to fall back to things like permutations. If your data set is really too small, then it's probably unlikely you're going to get an interesting p-value out of it, no matter how you do this, right? You just won't have enough evidence. So yeah, there's a question about whether we need all the outcome frequencies bigger than 0. That would be ideal. If the expected frequency is really tiny, then it may not make so much of a difference. Just one of the problems here is that when you compute the chi-squared statistic, the expected frequencies are down in the denominator here. And so if you have like a really tiny expectation, then you could start getting into trouble here that if it's hard to normalize these deviations. But yeah, I mean, some of this also depends on the kind of experiment that you're testing. So there might be cases where there might be cases where you don't, for example, have a lot of control over what people are answering, and so it might be hard to get people in these cells. But yeah, I mean, worst comes to worst, again, you can always just go back to permutation tests, and right, the kind of permutation test here is permutation is maybe not even the right word. You really would do like a kind of brute force simulation where you would take you would just generate from your null hypothesis, you just generate a whole bunch of data sets and measure what the chi-squared statistics are in those data sets, and use that empirically generated distribution instead of assuming that the sort of standard critical values are going to work. Okay. The next thing we'd like to talk about is what if we have multiple factors for each individual subject, right? So what if instead of just asking a single nominal question, we're getting multiple nominal responses from each person? What we'd like to do is test for some kind of interaction, right? Something like a correlation that says whether these two factors are independent of each other or not, right? What we want to know is, are these two responses we're getting, are they linked in some way that knowing one would actually let us predict something about the other question we're asking them? And so it turns out that we can. It's a very similar kind of test, but we're going to have to create a different kind of expected frequency distribution, and we're going to have to change the way we compute degrees of freedom. So the null hypothesis we're going to test here is whether the outcomes to these two different questions we're asking people are independent or not. And so remember back from our probability rules, if A and B are two events that are independent, the probability of both of them happening is just the product of them happening individually. And so this is the kind of null expectation we're going to test, right? Is that if we know how likely each of A's possible outcomes are and how likely each of the B possible outcomes are, right? And again, these are like two different questions, like the gender color example, something like that. Then we can compute for every possible combination of outcomes about how many should we expect, right? So this null hypothesis here is assuming that A and B are independent. And so the idea here is that we can generate these expected frequencies with this null assumption that A and B are independent, and then test whether that null assumption actually is consistent with the data or not. So the example we're going to do is that imagine you're trying to take a class, and there's you have a choice among 3 different professors to teach the class. And you have from the previous year, you have what we call a contingency table, which all this means is that this is just a table that counts up all of the combinations of outcomes from the previous year. And so you can see this is every number in here is a number of students. So there were 96 students that took the class with Professor 1 and got an A. There were 44 students that took the class with Professor 1 and got a B, and so on. The last column and row here are the totals among these. So 187 students total were with Professor 1, and 216 students total got A's. And so you can see that the data is kind of complicated. There's like different numbers of people in each class. There's different numbers of people getting each grade. And what we want to know is there, like, if we have a choice among professors here, if we want the best chance of getting an A, which class should we take, right? Or if we, right, or maybe a more general question is simply, are these professors grading with different distributions, right? So different professors here, right, are they giving a different fraction of people A, B's, C's, and D's? And so the null hypothesis here is that the classes and the grades are independent, that there's some probability of getting an A, there's some probability of being in Professor 1's class. The probability of getting an A in Professor 1's class is just the product of those two probabilities. So here we have two factors. And again, factors are like these different questions that we're asking, right? Or these different measurements that we're making. And these factors also have different numbers of levels. So there's 3 levels to our professor factor. There's 4 levels to our grade factor. So to figure out this null hypothesis, we're going to need to figure out the probabilities of each of our grades and the probabilities of being in each professor's class. And so we can do this pretty easily by just looking at these overall totals, right? So there's 434 students total, 216 of them got an A. And so what that tells us is that overall 49% of the students got A's, right? Just 216 divided by 434. So here's our grade distribution of grades. And so you can see these numbers sum up to 1, right? It's telling us how our students distributed across grades. And this is ignoring which class they're in. We can also do this across the rows. So this is showing us what fraction of students are in each of the classes, ignoring what grade they got, right? This is just, for example, 127 divided by 434. So here we have the distribution across classes. This is a probability distribution that sums up to 1. Here's a totally separate probability distribution that's over grades that sums up to 1. And so what we want to know is, to get these probabilities, all we used was this stuff at the edge of the table, just these total sums at the edge. We didn't actually use anything inside here, right? We're just using the totals. And so what we want to know is whether whether we can predict the values that are inside the center of this table from these external ones. Yes, I'm also just realizing now you can't see my mouse. I apologize for that. Okay, so if the null is true, we should be able to predict this value of 96 inside the table just by knowing the probability of being in Professor 1's class and the probability of getting an A. So in this case, we would, if the null is true, we should be able to predict this probability just by multiplying together 0.49 and 0.43. So to actually do this test, right, we need frequencies instead of probabilities, which just means we need to multiply everything by the sample size. There's a shortcut for doing this. If you have the row and column totals, which is just that you just take the row total times the column total divided by n, that'll give you something that's in the right units of participants, right? You could do row divided by n times column divided by n times n. And so one of the n's just cancels out. So what we can do here is that if we have these total number of students in each class and the total in each grade, we can then fill in the center part of this table under the assumption that this null hypothesis is true, right? So to get this 91.3, what we're doing is 187 times 216 divided by 434, right? So we're only using, we're just by using this stuff that's at the edge of the table, so this bottom row and this last column that are the totals, we're going to try to predict the stuff that's in the actual interesting meat of the table, right? And so we're making the assumption that all of the professors are grading the same way. And by doing that, we can predict what our frequencies should look like under that null hypothesis. So yeah, there's a question about how to do this in R. So you'll see this in the lab. Basically, all you need to do is, if you have the sort of tallies of how many people are in each class and the tallies of how many people get each grade, you just do what's called an outer product, which is just a multiplication of those that multiplies every pair of those values. Right. So what we would do here is, right, we need to multiply every possible number in the bottom row and every possible value in that last column together, and divide by 434. That'll give us the inner meat of this table. Okay, so now we're back in our sort of null hypothesis land, which is that we have our actual data, which is on top, right? Our actual observed data. And on the bottom, we have our null hypothesis. And so the null hypothesis here, again, is not that all of the outcomes are equally likely, right? The null hypothesis here is that the grades and the professors are independent. And so what that means is that, right, most people are in Professor 1's class. And so that means the expected number of people that are getting A's in Professor 1's class should be more than the number of people getting A's in Professor 2's class, just because there's more people in that class, right? So we're using what we actually measured in our data to get these totals. So that last column in that bottom row, that's coming from our actual data. We use what we actually got in our data to get these totals. And then the null hypothesis here is about the combinations. And so we can then test whether the counts in our real data differ from these combinations or not. And so all we do here is we're computing the same statistic, right? We're going to measure the deviations between each of our 12 outcomes, right? There's 4 times 3 outcomes here. And we're going to compute this chi-squared statistic. So, right, we take, there were 96 A's in Professor 1's class. We're going to measure how far away that is from the 93.1 that we expected, and so on for all these 12 different outcomes. And so this gives us a chi-squared statistic here of 32.97. Right, so the last thing, okay, actually, yeah, let's take a quick break for a quiz here. So the question is about this null expected table of frequencies that we're generating. Is this A, it can be computed before we collect our data. B, assumes all outcomes are equally likely. C, must contain only integer values, or D, none of the above. All right, what do people think? All right. Yep, I'm seeing some D's, which is the right answer, right? So, so A is the tricky one here, because usually this is true. Usually our null hypothesis we write down before we've looked at our data at all. But here we have to do this slightly weird thing where we actually want our null hypothesis to depend on the true distribution across each of our factors independently, right? So this is not a test. We don't have a null hypothesis about that, like most people should get A's or B's or something like that. Our null hypothesis is that the responses to the grade question and the responses to the professor question are independent. So to compute these null expectations, we actually need to first collect our data, get these total distributions of how many people total are in each class and got each grade. And then the null distribution is just about these combinations, right? The null expectations are just about the combinations of grades and classes. So we're not assuming that the outcomes are equally likely. And we usually won't get integer values to this computation. Okay, so the last step we need to actually figure out if this is a significant difference or not is we need to know the critical value. And to do that, we need to know the degrees of freedom. And so in a two-way chi-square test, the degrees of freedom are given by this multiplication. So they're basically the degrees of freedom of the first factor, which is the number of levels minus 1, times the degrees of freedom of the second factor, which is the number of levels minus 1. Right, so here there are 3 levels for the class outcome. There's 4 levels for the letter grade outcome. And so that gives us 2 times 3 equals 6. So we can then go look up, okay, this is a chi-squared statistic, has 6 degrees of freedom. The critical value here would be 12.59, and we're way above that, right? So we would reject the null hypothesis that the professor's grade using the same distribution. Right, so this test by itself doesn't actually tell us what the difference is, which is something we'll talk about a little bit today, and we'll talk about more in the next couple of weeks. But it just tells us there's some difference, right? So you could, if you just sort of inspect the tables, you can get some idea of maybe what's going on, right? Right, we can look for where we think these big deviations are. So right, so for example, you could see like Professor 3 here only gave out 50 A's. We would have expected 69 A's, right? And so, right, so you could look at each of these squares, right, to see sort of what could be driving this. But this statistical test itself doesn't actually test these like individual cells. It's just what we call an omnibus test, meaning that it says something is funky somewhere in this matrix. There's some kind of non-independence between the class and the grade. Okay, so just to write down the assumptions for this test. So first of all, again, we always have our assumption. This is randomly sampled independent data. We get a null hypothesis here just from the measured overall rates of each factor. So this is actually kind of a nice thing about the two-way test is we don't have to come up with a null hypothesis ahead of time. We just measure it from our data, right? So from the actual data distributions of the grade and the classes separately, we can then just multiply them together to get this null distribution. We also need a big enough sample size that the chi-square distribution is actually a good description of what our null distribution looks like. The requirement is basically the same as for the two-way test, that we want to have at least one observation in every cell, and ideally like more than 5 per cell. The requirement is basically the same because we're running the same test as in the one-way test. The degrees of freedom are just different here. In practice, this becomes a little harder for the two-way test just because there's so many more cells, right? So we're dividing up here, we're taking our subjects, we're dividing them in this example into like 12 different categories. And so because of that, it can become hard to actually get enough subjects in each of those categories. But at least in principle here, it's the same kind of idea that we just need to have enough subjects in each of our cells here that we can actually get a chi-square distribution that has sort of properly converged to the true distribution. Okay, so the last section of class today is thinking about how we would actually report the result of a chi-square test and how we'd actually interpret it. So in this example, we said that the professor and grade factors are not independent. And we got a p-value out of this, right? Or we at least know that the p-value is less than 0.05. So that tells us that we're pretty sure there is a difference. But it doesn't tell us anything about how strong that association actually is, right? It tells us that we think professor and grade are not independent from each other, but it doesn't tell us whether there's actually a strong association. Like maybe there is a very tiny difference in the way different professors grade, but it's not like a meaningful difference, right? It's statistically significant, meaning we can detect it, that it's different from the null, but it's not, you wouldn't actually make any decisions in your life based on it. So there's not a super easy way to visualize these kinds of associations, right? We can't do a scatter plot here. You can kind of like color in a table like as a heat map, which sometimes works. But there is something we can compute. And so what we want to know is basically to what extent does knowing one factor determine something about the other factor? So for example, if this was like a really extreme case where one professor is giving only A's and another professor is giving only B's, then one factor would entirely determine the other, right? If I knew which grade you got, I could tell which class you're in, and vice versa. So what we want to know is sort of on a scale of totally independent to completely determine each other. Where are we on that scale? So we can use this measurement called Kramer's phi. So yeah, we will often write this with the Greek letter phi, which unfortunately looks different, like in different fonts. So you'll see it written a few different ways. It's also sometimes called Kramer's v, and it's basically something like we'll see here. It's going to be interpreted kind of like a Pearson correlation. And it's really easy to compute once you have the chi-squared value. All you need to do is this. So you take your chi-squared value, divide it by n, and divide it by the minimum degrees of freedom of your rows or your columns, and then you take the square root of that. So in the example we just did, right, the minimum degrees of freedom here is 2 because there were 3 professors, and so that the degrees of freedom for the rows here is 2. And so our Kramer's phi would be the square root of our chi-squared value divided by n times 2, which is 0.19. So this thing is pretty easy to compute if you've already gone through all the trouble of computing this chi-squared. And so it's very similar to a correlation, right? In the same sense that it goes, that it is telling you something from like no relationship up to a perfect deterministic relationship. It doesn't have it can't be negative, right? Because there's no order to these nominal categories. So, like things can't be negatively correlated because there isn't like a negative direction here, right? So things can either be unrelated, which is 0, they're independent of each other, or up to 1 is they're completely determine each other. There is like a p-value that's associated with Kramer's phi, but it's just the same one as that's associated with the chi-squared statistic, right? So you don't have to do a separate statistical test on this, right? This is significant if the associated chi-squared statistic is significant. So this is a kind of nice standardized score, but it doesn't give us. It's not useful for computing a p-value. It doesn't tell us something about whether we're significantly different. But it does give us a useful measure of effect size that's on an interpretable scale, right? So it can, and again, right, we got 0.19 in this case, which is basically telling us that there is, sort of a moderate relationship between the professors and the grades. It's not super strong, right? It's not, if you're in Professor One's class, it's not going to determine your grade, right? There's still a lot of other variability in the data. But right, so on a scale of 0 to 1, we're like 20% in or something, right, of how related these things are. So these are often, in some ways, these kinds of effect size measures are more useful than p-values in the sense that they tell you how big the effect actually looks in your data. Right, a p-value is useful for knowing whether you actually have confidence to say that effect is real, right? But in some sense, like these kind of effect size measures or things like confidence intervals are maybe more useful for like actually making decisions about things. Okay, so we'll do one more quiz. So we use this Kramer's phi, A, when we don't know the degrees of freedom, B, when our sample size is less than 5, C, for one-way chi-squared tests, or D, to measure association between nominal outcomes. All right, you can go ahead and respond. Okay, great. Yep, I'm seeing some Yep, seeing D's, which is great, right? So that's where Kramer's phi is measuring association between nominal outcomes. It's not useful for any of these things in A, B, and C. And oh, you actually can see my mouse. Good. I was going crazy for a second there. So yeah, so we can't use if we don't know the degrees of freedom or we have missing data or something, then none of the stuff we talked about today would work. When sample sizes are really small, these chi-squared statistics and any of their associated effect sizes are not going to be super useful. And this is not relevant for one-way tests, right? This is really just about association between two outcomes. And so it's not, this can't tell us anything useful for a one-way test. Okay. So we could think about when we would actually want to use this kind of chi-square test. So first of all, if both of our outcomes and predictors are nominal, then we sort of have to use these. Again, we could fall back on things like permutations and simulations, right? But the only like distribution, the only sort of closed form distribution we could use for nominal outcomes would be these chi-squareds. But again, just like with the rank tests, when we're talking about rank tests and scale data, you could choose to use these chi-squared tests even if we have more complicated kinds of data, right? So even if we have measurements that are ordinal or scale measurements, we could turn them into nominal measurements if we want to. And so there's an obvious downside to this, which is that it's going to reduce our power, right? So remember we talked about this last time about power efficiency, that anytime we're throwing away stuff in our data and sort of making fewer assumptions about our data, it's going to make it harder to detect real effects. Right. And so this is usually going to be a bad thing. And so the question is, why would we do this? And usually we wouldn't, but sometimes we do this because we're not sure how to actually interpret the data that we have. So it could be the case that we collected data which is theoretically supposed to be scale data, but really the values are not super comparable, right? It might be that whatever this sort of construct is that we're measuring, really the only information we're getting from people is whether they fall into a couple different categories. It doesn't really tell us something about like deviations within that category. So, you could think, for example, people, when they try to, people might represent their political orientation on like a 2D plot. You've probably seen some of these online. And so there's a kind of scale version of that, which is that you actually, your political opinions are actually like a 2D coordinate somewhere in this space that has an X and a Y coordinate. Right. There's a few different versions of these, but the axes are usually something like sort of like social conservative to liberal and economic conservative to liberal. Right. So you could think that you actually have like a scale measurement of each of these values. Or maybe you think that really all that matters is like which quadrant you're in, right? So you could be in the positive XY quadrant. You could be in the negative X positive Y quadrant, right? So maybe the actual values here are like not super meaningful, and which quadrant you're in is really the only thing that we would expect to be relevant to your behavior or something. So we might choose to throw away this scale information and say, really the only thing I trust is which quadrant you're in. I don't really trust that we have accurately measured where you are in that quadrant. And so, again, this is sort of a balancing act. You want to use all the information in the data that you think has actually been measured in a robust way. You want to make all the assumptions that you think are reasonable. That will give you the most power, for example. Right. But if you're uncertain about things in your data, if there's assumptions about the data you're unsure are true, you may want to choose to not use that information in your statistical test. It means, again, it's going to mean that you're going to lose some sensitivity, but at least you're not going to get an invalid p-value, right? Making assumptions that are not true about your data is going to give you a p-value that's not particularly meaningful. And so, again, it depends a lot on the situation. You need to really have some expert knowledge in the domain that you're studying to know what the right way is to do this. All right, I'm just going to move on to a final summary now. If people have any other questions about any of the material from the class, feel free to ask. So, right, in summary, we talked today about these chi-square tests that are non-parametric tests that only require categorical data. They don't require us to do any math. All that we need to do is be able to count in our data set how many of different outcomes we got. The one-way chi-square test is for a single factor, and we can measure how many outcomes we got from that factor and whether it's consistent with some kind of null distribution. And whereas the two-way chi-square test is testing whether two different factors are associated with each other or are independent, right? And so for this two-way test, our null hypothesis is that we can predict the combinations of these two factors just by knowing the distributions of each of these two factors independently in our particular data set. We also talked about this Kramer's phi, which is a way of measuring how strong this association is. And so it's kind of nice to know both the p-value, which is whether we think there is an association that's different from 0 or not, as well as this measure of how strong we think that association is. And so this chi-square test is super general, right? That really the only sort of potentially problematic assumption here is that we need enough data in each cell. But even that, it's pretty, we really only need like at least a few observations in each outcome cell, which is not that hard to get. And so that means that the assumptions for this test are really easy to satisfy, which is great. The problem is that because there's so few assumptions here, because it assumes we can't actually do math on our data, it means that the power can tend to be low. And exactly how bad the power efficiency is depends on the situation. But so you might, right, these are sort of like the last resort kinds of tests. If you don't want to go to like permutations and simulations, right? Permutations and simulations are the kind of like least assumption tests. These chi-squared ones just have slightly more assumptions in them, right, about the sample size. All right, great. So yeah, if there's no more questions, I think we'll finish for today. Please try to get in last week's homework when you can. Next week's homework is up. I'll have the lab up later today. The lab includes, the first half of the lab is on this stuff. The second half of the lab includes some stuff from Thursday, but you could get started on it if you'd like. Great, yeah, feel free to, me and the TA's office hours are going on as scheduled. Feel free to also email us to set up other times to talk. Great, I hope everyone's staying safe. Please keep in touch.